Picture this. It's 8:32 in the morning on May 18th, 1980. You're standing on the ridge overlooking Spirit Lake, Washington. The air is crisp. The mountain looms ahead of you. Massive, white, impossibly beautiful. Mount St. Helens, and then without warning, the entire north face of the mountain simply disappears. This is one of the most violent volcanic eruptions in recorded American history. The largest landslide in recorded human history collapses at once. The pressure that had been building for 2 months is suddenly, catastrophically released. A lateral blast of superheated gas, ash, and rock explodes outward at 300 miles per hour, flattening 230 square miles of old-growth forest like a carpet of toothpicks. The ash column punches 80,000 feet into the stratosphere. Pyroclastic flows race down the mountainside at hurricane speeds. And then come the lahars, rivers of volcanic mud, thick as wet concrete, thundering down river valleys toward towns, highways, and bridges. 57 people died that day. The mountain lost 1,300 feet of elevation in minutes, and the Pacific Northwest was changed forever. But here's what most people don't realize. The 1980 Mount St. Helens eruption was just one chapter in a much longer story. And Washington State has 5 active volcanoes that are still writing that story right now. Welcome to one of the most volcanically active regions in North America. This is the story of Washington's Cascade volcanoes, where they came from, what they're capable of, and what happens when the next one wakes up. To understand why Washington State sits on top of one of the most dangerous active volcano systems on the planet, you have to go to the bottom of the Pacific Ocean. To see where it all begins, you have to leave shore and head 150 miles out into the Pacific, to a tear in the seafloor called the Juan de Fuca Ridge. This is an intermediate spreading rate ridge, 5 to 10 centimeters per year, a remnant of the much larger Pacific Farallon Ridge. Here, 2 pieces of the Earth's oceanic crust are slowly pulling apart. Hot magma wells up from the mantle, cools, and hardens into brand new seafloor. The ridge is famous for its hydrothermal activity, including black smokers, vents that spew superheated, mineral-rich water, fueling bizarre deep-sea ecosystems through chemosynthesis. Axial Seamount, the most volcanically active site on the ridge, has been closely studied by scientists and provides crucial data on plate tectonics and seafloor spreading. One of the most researched mid-ocean ridges on Earth. That dense oceanic crust, the Juan de Fuca Plate, then starts a slow crawl east, moving only as fast as your fingernails grow. Stretch that motion over millions of years, and it becomes the setup for something catastrophic. This plate moves eastward and subducts beneath the North American plate at the Cascadia Subduction Zone, part of the Pacific Ring of Fire. Eventually, the Juan de Fuca Plate reaches the edge of North America and runs out of room. With nowhere else to go, it dives, plunging beneath the continent along that boundary known as the Cascadia Subduction Zone. As it sinks deeper, the immense pressure squeezes water out of the minerals in the plate. That water seeps upward into the overlying mantle wedge and, here's the crucial bit of geology, lowers the melting point of rock. Rock that should remain solid suddenly begins to melt. Magma is born. It rises. It pools in underground reservoirs. And when enough of it accumulates and finds a path to the surface, it erupts, constructing the chain of volcanoes we know as the Cascades. The result is the Cascade Volcanic Arc, a line of volcanoes stretching more than 700 miles from Northern California through Oregon and Washington and into British Columbia. Every active volcano along this arc owes its existence to that same slow, relentless engine grinding away beneath the surface. And sitting near the center of this chain is Washington, home to 5 of the most dangerous peaks in the entire arc. This is why Washington's volcanoes are fundamentally more dangerous than the broad, gentle shield volcanoes of Hawaii. Hawaiian magma is runny. It flows easily, spilling out in glowing rivers of lava. Cascade magma, by contrast, is rich in silica and thick like paste. It traps gases, pressure builds, and when it finally lets go, it doesn't pour. It explodes. If you had to pick one volcano that proves geology is not ancient history, but present tense, it's Mount St. Helens. Before May 18, 1980, Mount St. Helens was called the Mount Fuji of America. Symmetrical, elegant, a perfect cone rising to 9,677 feet. Then, on March 27, 1980, after 123 years of quiet, it coughed. Small steam explosions dusted the summit. Earthquakes swarmed, and the north flank of the mountain began bulging outward at up to 5 feet per day. USGS volcanologist David Johnston was monitoring the mountain from a ridge 5.7 miles away on the morning of May 18th. At 8:32 a.m., a magnitude 5.1 earthquake triggered the catastrophic collapse of the north face. Johnston's last transmission: Vancouver, Vancouver, this is it. He was killed instantly by the lateral blast. The catastrophic collapse of the entire north face in the largest landslide in recorded history. It rocketed downhill at up to 155 miles per hour, filling the North Fork Toutle River Valley with debris up to 600 feet deep. This massive slide released high-pressure magma, unleashing a sideways blast that roared outward at over 300 miles per hour, potentially supersonic, flattening 230 square miles of forest in minutes. The Mount St. Helens eruption unleashed energy equivalent to 1,600 Hiroshima atomic bombs. It was the deadliest and most economically destructive volcanic event in U.S. history. Ashfall reached 11 states. 3 billion board feet of timber were destroyed. It stands as the most studied natural disaster and volcano eruption in American scientific history. And the lessons it taught us about geology changed the field forever. Melting snow and ice fueled volcanic mudflows, wet concrete lahars that destroyed 27 bridges, 200 homes, thousands of wildlife, elk, deer, bears, and 12 million fish. Economic damage topped $1.1 billion, about $3.5 billion today. The mountain summit dropped 1,300 feet, carving a mile-wide horseshoe crater. But Mount St. Helens wasn't finished. Between 1980 and 1986, smaller eruptions built a lava dome inside the crater. It stirred again from 2004 to 2008, doubling the dome's size. Since 1986, a new glacier, Crater Glacier, the youngest on Earth, has formed in the shaded crater. The blast zone has become a natural laboratory for ecological recovery, where snow-protected plants survived and now thrive. Today, Mount St. Helens is the most seismically active volcano in Washington state. It is the most likely active volcano in the entire Cascades to erupt again, and the earth beneath it never truly stopped moving. While St. Helens grabs headlines for its fury, Mount Rainier looms as the silent heavyweight, the Cascades' most dangerous threat due to its sheer mass of ice and proximity to millions. An active stratovolcano and one of the world's 16 decade Volcanoes, it towers as the tallest, most topographically prominent peak in the contiguous US, with its official summit at Columbia Crest, 14,410 feet, though recent ice melt may have shifted the true high point to the southwest crater rim. Rainier is the most heavily glaciated peak in the lower 48 states, featuring 28 named glaciers, plus unnamed snowfields, including the largest by area, Emmons Glacier, and by volume, Carbon Glacier, and a summit crater network of volcanic glacier caves nearly 2 miles long, carved by geothermal heat. That ice, over 1 cubic mile, is not scenery. It is a loaded weapon. The mountain feeds 5 major rivers: Cowlitz, Puyallup, White, Nisqually, and Carbon. When geologists and emergency managers talk about natural disasters in the Pacific Northwest, Mount Rainier dominates the conversation. A major eruption, or even a large earthquake triggering a slope collapse without any eruption at all, could mobilize that ice into lahars of almost unimaginable scale. Lahars are volcanic mudflows, not thin floods, but churning rivers of rock, ash, and ice melt with the consistency of wet concrete. They move fast, up to 60 miles per hour. They fill valleys. They bury everything. We know this isn't hypothetical. It has already happened. Roughly 5,600 years ago, the Osceola mudflow, one of Rainier's largest, swept more than 60 miles from its flanks, burying what is now Auburn under up to 350 feet of deposits across 212 square miles. About 500 years ago, the electron mudflow raced down the Puyallup River, triggered not by a major eruption, but by hydrothermal weakening and slope collapse alone. Today, cities like Orting, Sumner, Puyallup, Fife, and Enumclaw, a combined population exceeding 150,000, with 3.7 million at risk in Puget Sound lowlands, sit directly in Mount Rainier's lahar hazard zones. A lahar racing down the Puyallup River would give Orting roughly 30 to 45 minutes to evacuate. Precious little time for 20,000 people with limited road exits. Of all the natural disasters that could strike the Pacific Northwest, a Mount Rainier lahar ranks among the most devastating and the least discussed outside geology and emergency circles. Rainier is the volcano that keeps scientists awake at night. Head north from Rainier through the Cascades and Mount Baker emerges, the northernmost volcano in the contiguous United States and the highest peak in the North Cascades at 10,781 feet, third highest in Washington, fifth in the Cascades. Its ice-shrouded profile dominates skylines from Greater Vancouver to Seattle, holding the heaviest glacier cover of any Cascade volcano after Rainier, with more ice volume than all others, excluding Rainier, combined. But Baker has a secret it doesn't bother hiding. It vents constantly. The peak contains 2 craters, including the ice-buried Carmelo crater at the summit and the active, steaming Sherman crater just below. Sherman hosts one of the most active hydrothermal systems in the entire Cascade Range, the second most thermally active volcano in the Cascades, with steam, sulfur dioxide, and hydrogen sulfide pouring continuously from fumaroles, some over 130 degrees Celsius. The surrounding ground has been chemically transformed by acidic fluids, converting lavas to weak, white to yellow clay, exactly the kind of rock weakening that makes a volcanic flank vulnerable to sudden collapse. In 1975, Baker's thermal output jumped tenfold within weeks, melting half of Sherman Crater's glacier, creating hot crater lakes, one at 34 degrees Celsius, and coating snow with ash. The USGS issued a hazard warning and partially drew down Baker Lake Reservoir downstream to mitigate flood risk. The increased activity continued for years without a full eruption, a powerful reminder that an active volcano doesn't need to erupt to be hazardous. It just needs to be unstable. The current cone is young, less than 140,000 years old. The last eruption was likely 1880, though an 1843 event triggered major lahars. And with its extreme snowfall, holding the world record at 1,140 inches, 1998 to 1999 season, averaging over 600 inches annually, significant glaciers feed the Nooksack River toward downstream communities like Bellingham. Baker carries lahar risks that few outside the geology community take seriously enough. After Baker, the story of Washington's volcanoes takes a turn into the shadows. Glacier Peak is the most remote of Washington's 5 active stratovolcanoes. Located deep within the Glacier Peak wilderness, it sits 70 miles northeast of Seattle, famously hidden from major population centers by surrounding high ridges. No roads within 15 miles, no visitor centers, no famous postcards. And geology tells us that may be exactly why it has been so dangerously overlooked. One of these 5 active volcanoes has a secret that could change everything you thought you knew about volcanic risk in Washington state. And almost nobody is talking about it. At 10,541 feet, Washington's 4th tallest peak, Glacier Peak is a small stratovolcano by volume, rising just 1,600 to 3,200 feet above its ridge. But its explosive history dwarfs most neighbors. Along with Mount St. Helens, it's one of only 2 Washington volcanoes to produce massive eruptions in the last 15,000 years. The event called Layer G, approximately 13,100 years ago, was 5 times larger than St. Helens' 1980 blast, sending an ash column over 100,000 feet into the stratosphere. Tephra found as far as Montana, Wyoming, and Alberta. These were not local disasters. They were continental ones. Its most recent significant eruption was approximately 300 years ago, approximately 1700 AD, and USGS classifies it very high threat for lethal lahars reaching Puget Sound. Today, with 11 to 15 glaciers, Honeycomb, Chocolate Cool, descending its flanks, shrinking a third by 2025, potentially glacier-free in 50 years, Milk Lake Glacier vanished in the 1990s. It's monitored by USGS Cascades Volcano Observatory like St. Helens and Rainier. In a major eruption, Sauk and Skagit River drainages face devastation, threatening communities and the Skagit watershed supplying regional drinking water. The Pacific Crest Trail skirts it for 60 rugged miles. Climbers tackle Sitcomb Glacier or White Pass routes. Settlers didn't recognize it as a volcano until the 1850s. It wasn't mapped by name until 1898. Most people have never worried about Glacier Peak. The geology suggests that may be exactly the wrong instinct. Deep in the southern Cascades, far from Glacier Peak's hidden wilds, stands Mount Adams, completing Washington's quintet of high-threat volcanoes. Mount Adams, often called the Forgotten Giant, due to its remote location, is the largest volcano by volume in Washington and the second highest peak in the state at 12,276 feet. A massive, active stratovolcano with a base 18 miles wide and a broad, flat summit formed by eruptions from several separated vents, it dominates a volcanic field of over 120 smaller cones. It supports 12 named glaciers, including Adams Glacier, the second largest in the Cascades after Rainier's Carbon Glacier, Adams has generally produced less explosive eruptions than St. Helens, more effusive lava flows and cinder cones than catastrophic blasts. But Adams has its own strange story. In the late 19th and early 20th centuries, its summit was actively mined for sulfur, one of the few cases in American history of commercial mineral extraction from an active volcano. Workers harvested sulfur-rich fumarolic deposits from a smoking, thermally active volcanic summit at over 12,000 feet. The geology of Adams made it a literal chemical resource. From a hazard standpoint, Adams is not considered as immediately threatening as Rainier or St. Helens, though a small earthquake spike in September 2024 raised eyebrows. Its most recent major eruption was roughly 1,000 years ago, and USGS ranks it high threat primarily for lahars from its weakened, hydrothermally altered rock core collapsing into the White Salmon and Klickitat drainages, impacting communities like Trout Lake. Adams is quiet, but in geology, quiet is never the same as finished. With Adams' quiet bulk behind us, one question lingers over all five. What happens next? So let's talk about what you came here to think about. The next eruption. The USGS currently ranks Mount St. Helens and Mount Rainier as two of the highest threat active volcanoes in the continental United States. The combination of eruptive history, magmatic activity, ice volume, proximity to population centers, and downstream lahar risk puts them in a category of their own when it comes to natural disasters threatening the American Pacific Northwest. For Mount St. Helens, a future eruption is a matter of when, not if. The same subduction-driven magmatic system that produced the 1980 event is still active. USGS models suggest a future event could range from a modest dome-building episode to a significantly larger explosive eruption, with ashfall affecting much of eastern Washington, northern Idaho, and beyond, depending on wind. For Mount Rainier, the nightmare scenario doesn't require a full eruption at all. A large earthquake and the Cascadia Subduction Zone is overdue for a megathrust event of magnitude 8 or 9 could destabilize the thermally weakened interior of the mountain and trigger a catastrophic sector collapse. The resulting lahars would reach the Puget Sound lowlands in under an hour. No lava, no ash column. Potentially very little warning. USGS and the Pacific Northwest Seismic Network operate a world-class monitoring system around all 5 Washington volcanoes: seismometers, GPS stations, tilt meters, and gas sensors. Any significant precursory activity triggers escalating alert levels. The science is extraordinary. The challenge is time, and whether the people living in lahar zones have genuinely internalized the risk and know their evacuation routes. Washington State has documented at least 22 eruptions since 1820. The Earth's geology doesn't take breaks. On a human timescale, eruptions here are infrequent. On a geological one, they are relentless. Here's the thing about volcanoes. They're not just disasters waiting to happen. They created the Pacific Northwest. Cascade Valley's fertile soils, centuries-old volcanic ash, glacier-draped peaks drawing millions, built by millions of years of eruptive cycles. Washington's rivers, minerals, and geology, all products of this relentless creative force. These 5 volcanoes aren't problems to solve. They are the landscape. The USGS Cascades. Volcano Observatory in Vancouver, Washington monitors these peaks with world-class rigor. Scientists who have given their careers, and in the case of David Johnston, their lives, to understanding the geology of these mountains. They are not alarmists. They are the reason we have any warning systems at all. The Cascade volcanoes will erupt again. Maybe not tomorrow, maybe not in our lifetimes, but the Juan de Fuca plate is still moving. The Earth's mantle wedge is still melting. The magma is still rising. And when it does, the story of Washington State's Cascade volcanoes will enter a new chapter, preserved in layers of ash and stone, waiting to be read by whoever comes next. If this video gave you a new respect for the ground beneath your feet, then we've done our job, and we need your help to keep doing it. If you learned something today, hit that like button right now. It takes 1 second, and it tells YouTube this video is worth sharing with more people who love Earth science just as much as you do. Drop a comment below and tell us, which of Washington's 5 active volcanoes do you think is the most underrated threat? And which one do you think will erupt next? There's no wrong answer. This is exactly the kind of conversation we're here to have, and I personally read every single comment. And if you haven't already, subscribe and hit that notification bell so you never miss a new episode. We've got more geological epics coming your way, the kind of stories that remind you just how alive this planet really is. Thank you so much for watching.